Given an array of balloon values. Burst one balloon at a time, each burst pays left neighbor times value times right neighbor, with missing neighbors counting as 1. Collect the largest possible total after every balloon is gone. Example nums 3, 1, 5, 8. Burst the 1 first, 3 times 1 times 5 is 15. Next burst 5, 3 times 5 times 8 is 120. Total 135. Burst 3, 1 times 3 times 8 is 24. Total 159. Last burst 8, 1 times 8 times 1 is 8. Output 167. The maximum total is 167. You are given a row of balloons, each with a number. Popping a balloon earns points equal to its value multiplied by its left and right neighbors. If your immediate instinct is to look for the best balloon to pop first, you will quickly spiral into chaos. The moment a balloon pops, its neighbors merge to form a completely new partnership. This dynamic mutation makes it impossible to divide the array into independent subproblems. To conquer this hard problem, we have to play the tape completely in reverse. Instead of choosing which balloon dies first, let's look at a specific range of balloons and pick which one dies absolutely last. Think about what this means. If a balloon is the last survivor in its range, every single balloon to its left and every single balloon to its right has already been wiped away. This leaves our survivor standing directly next to the original outer boundaries of the range. This backwards perspective unlocks a massive architectural win. Because balloon I is the last to burst, it stands as an unpoppable anchor while the left and right sides are being cleared. This means the left subproblem can be solved completely independently of the right subproblem. They are separated by a brick wall. No pop on the left can ever alter a neighbor on the right, turning a chaotic chain reaction into perfectly isolated chunks. The total coins we earn by nominating balloon I as our final survivor is a simple three-part addition. First, we collect the coins from completely clearing the subproblem to its left. Next, we add the coins from completely clearing the subproblem to its right. Finally, we add the coins from popping balloon I itself. Since it is the last balloon left in the range, its immediate neighbors are guaranteed to be the outer boundary walls at left -1 and right +1. To write this code, we build our answers from the bottom up using interval dynamic programming. We start with a scanning window of length 1, calculating the best scores for every single balloon. Then we widen the window to length 2, length 3, and keep using smaller cached subproblems to solve larger sections immediately. We expand this window until it spans the entire row, giving the maximum score with O of n cubed efficiency. Let's write out the full solution code. We start by allocating a new array that is padded on both sides by two imaginary, unpoppable balloons with a value of 1. This prevents us from ever throwing an out-of-bounds error when checking neighbors, and ensures our edge balloons have clear boundaries to multiply against. Next, we initialize a two-dimensional matrix called dp. The cell at dp left-right will store the absolute maximum coins we can extract from the subrange stretching from index left to index right. To fill this table systematically, we spin up three nested loops. The first dictates the widening length of our viewing window, the second crawls that window across our array, and the third tests every single balloon inside that window as our final survivor. Let's watch the engine run for a window of length 1. When our window lands on our second index, it isolates the balloon with value 1. Since it is the only balloon in this window, it is forced to be the last survivor. The left and right subproblems are empty, costing 0. Popping it gives us its own value multiplied by its immediate outer neighbors, 3 and 5, giving us 15 coins. We lock that score into dp22. The code repeats this for every single individual balloon. Now see the true power of dynamic programming as our window widens to a length of 3, analyzing the subrange 3, 1, and 5. If we test balloon 5 as the absolute last survivor of this group, we do not recalculate how to pop 3 and 1. We look directly at our matrix to grab the pre-calculated maximum score for clearing that left subproblem, which is 30. We add that to the coins earned from popping our survivor between the outer walls, 1 and 8, giving us 70 coins. But 70 is only one candidate for DP13. The loop also checks using 3 as the last survivor, which gives 159, and using 1 as the last survivor, which gives 51. The maximum is 159, so that is what we store in DP13. Our window expands one final time to cover the entire length of our original array. It evaluates every possible candidate to be the ultimate final balloon standing on the entire stage. The moment this final cell finishes its comparison loops, it holds the absolute mathematical maximum coins achievable. The function returns this value, and we have elegantly solved a brutal hard problem by playing the timeline perfectly in reverse. Let n be the number of balloons. Time is O of n cubed, there are O of n squared interval ranges, and for each range we try every possible last balloon. Space is O of n squared for the DP matrix, plus a linear padded array. Function max coins takes the original balloon values. Store the number of real balloons as n. Create the padded array, already filled with boundary value 1. Copy the input balloons into the middle positions. Create a zero-filled DP matrix for every left and right boundary. Grow the interval length from one balloon up to the full array. Slide that length window across every possible left boundary. Compute the matching right boundary. Try each balloon in this window as the last survivor. Start with the best cached score from the left and right subproblems. Add the final pop score using the two outer walls and balloon I. Keep the best candidate for this interval. Return the answer for the full original range.